Raz, dwa, trzy. Jacku, jak tam u ciebie? To będzie po angielsku, tak? To Jack, how is going?
Let me interface with you in English.
Dobrze, wielkie brawa dla Jacka.
When you ask Google this, can Python support threads? It's pretty easy to come across answers like this one, that it doesn't. Let's go back in time. Let's go back to the year 1992. This is me, believe it or not, in 1992. Here you can see Java and JavaScript in 1992. In case it's not obvious, yes, they didn't exist back then. Here you can see CPUs that you could just grab off the shelf in any computer store for your personal computer in 1992 that have CPUs that have multiple cores. And yes, in case it's not obvious, they didn't exist back then, no matter in Poland or USA. And here you can see CPython in 1992 existing, yes, and with threading support. So this is clearly false. And this has been false since 1992. It continues to be false. How about this one? Is it true? Who thinks it's false? Ooh, that's surprising. Yes, it is false. We can discuss it later. How about this one? Okay, so obviously it's the third one, so it's obvious it's true, yes. But why is it true? What are the implications? Let's talk about it a little bit more. Let's discuss it later. Thank you. Anyway, okay. So for those of you that do not know me, I'm Jacek Kołodziej. I run long distances. I walk across mountains. Sometimes taking pictures. I walk from one metal show to another too, and also I live with these two cat brothers. And as for my day-to-day, I'm a principal software engineer at Allegro, where I'm working with the teams. Responsible for searching, for listing items, for the item page, for recommendations, and quite a few other things. And yes, we do use Python extensively. Each time you search for an item on Allegro, by default, you interact with some Python code underneath. But let's go back to the GIL. To go back to the GIL, we need to talk about quite a few things before that. So let's warm up. GIL is, of course, related to parallelism, but what is parallelism? Parallelism is when you execute your code physically in parallel. What I mean by that? You need to run more than one thread on more than one core. You physically need to have multiple cores to achieve parallelism. In contrast to concurrency, which is an illusion of parallelism, and you can have concurrent execution on a single core easily. What are threads? To talk about threads, it would be easier to start with processes. So what is a process? It's an instance of your application. It's a unit of execution of your code. And a single process is one or more threads. All the process has one. Ooh. No, that's not needed right now. A single process has like one has a shared memory, so all the threads share memory within a process. Oh, sorry, all threads of a process share memory. And in the case of CPython, and within the scope of this presentation, I will be talking about POSIX threads. What I mean by that? There are threads that you can call system ones, or kernel ones, or native, or POSIX. These are all basically the same within the scope of import threading in CPython, as opposed to all the other kinds of concurrency, meaning green threads, greenlets, asynchronous coroutines, and there are myriads of others. And back to threads, they can, at any given point in time, they can be in a state. They can be currently running, they can be ready to be run, or they can be waiting or be blocked by the system. Other things that are strictly related to computer science but are needed for us to talk about the GIL are logs and system calls. So these are what we call primitives. Yeah, logs. What are logs? These are tools for us to prevent something called race conditions. Each time we have one or more thread that access a single shared resource, there's an option, there's a possibility of our program having a race condition. It depends on what our program does, but each time you need to consider it. And logs is a log is a tool that you can use to prevent that from happening. So if there is a shared resource, you can guard it with a log. They are also called mutexes. So this is a shortcut from mutual exclusion of access to the resource. And a log can be locked or held, and then it can be unlocked or released. System calls are a separate kind of primitives, let's say, in a kernel, because a log is part of an API of a operating system kernel, as well as system calls are. This is an API for quite a few services provided for our programs by the operating system. For example, I/O access, including disk access or networking access, or putting something on our screen also. These are also system calls. Controlling other processes, and there are multiple others. And some system calls can be blocking. For example, I/O access is blocking, or even something as simple as sleeping is a blocking system call. What is important to realize is that while our Python program is waiting for a system call to complete, it doesn't need to hold the GIL. This is very important for the rest of our presentation. Another strictly related thing in CPython is memory management. The very, very core concept in CPython is managing memory by something called reference counters. So each Python object managed by CPython has a number attached to it. The number signifies how many references are there to that object. And this is a very, very simple and often very, very effective mechanism for managing memory. But there's a caveat. Each reference counter is a shared resource. So all threads that has access to some object, a reference counter for that object is a shared resource among these threads, and as such needs locking. There's also a mechanism for garbage collecting in CPython. It's only used for detecting circle dependencies, because otherwise you'd never release memory for circularly referenced objects. Another option how to manage memory in computer science is like more robust garbage collector for example, tracing garbage collector, and of course, this is like more powerful, but also significantly more complex than just reference counters. And of course, we have tracing garbage collectors in JVM languages or C# or many others. Yeah, and the final concept, completely different, let's say, is what is bytecode in Python. Yeah, the question about Python, is it interpreted or is it compiled? The answer is yes. But what is bytecode? When you execute Python, any Python program, first it goes through compilation stage, which compiles this code into bytecode, which for, let me give you a very, very simple example. If you take this code and you compile it, you can do it visually by using the this module, DIS. The bytecode for that code looks like this. Don't worry about memorizing it, it's just for the presentation. But after that, after the Python code is compiled into bytecode, it then goes to interpreter and is executed, meaning it's interpreted here. Whew. Sorry. Did you notice the finally word? First things first. GIL comes from Global Interpreter Lock. And what does it mean? Of course, it protects us from race conditions to quite a few resources. First, I already talked about it, reference counters, but also like C mutable Python data that is mutable on the C level. So not only dictionaries, lists, and so on, but also strings, also tuples, also integers, which can be muted from the C code underneath. Some internal global state that is there in all your Python processes, and also atomic APIs of like basically the C API. And it also gives developers of C extensions the possibility of using this very simple memory management mechanism to be able to write their software like in more basic way. Because they can just assume the GIL exists and don't worry about quite a lot of quite a big scope of memory management. Anyway, I already said that holding the GIL is not needed always. It's not needed when we are accessing I/O. So wherever our code needs to access some I/O, for example network, for example disk, it can just drop the GIL for that time. Whenever our code interacts with objects that are not Python objects, so whenever we are using, for example, NumPy, the GIL can be dropped, and it is dropped by NumPy for us. Yeah, so basically there are scenarios that the GIL doesn't need to be held. Okay, this is a part of the presentation that is pretty dense, and it's not here. It's here to demonstrate how the GIL works, but don't try to memorize what happens with the GIL. It's only there to show you that it can be like expressed on a presentation like this, pretty much without code, and also to that the GIL can be reasoned about in almost simple words. So either fasten your seatbelts and witness it, or take a nap, up to you. So quick warm up, just a very simple scenario where we have one single thread that is simply run and is running. This single thread executes some code on our CPU. Life is simple. And then some I/O happens. For example, we want to open some file and read from it. And so at that point, the thread is waiting for the I/O to complete. Scenario 2 is something different. We have two threads that will try both to be run and access our CPU basically. So as before, the first thread runs for some time, then we spawn a new thread, and at this point in time, this thread waits for the system scheduler to choose it to be run on a CPU. It's entirely up to the operating system when this thread will start. It's not CPython that governs this. It's not CPython that chooses which thread which will have the chance to run. At some point after the operating system, after kernel chooses the thread to be run, then it has some control, but not. But the starting point is within the realm of the kernel. So we are creating a new thread. It waits for the system kernel to choose it to be run, at this point it starts to run. First thing it does, it checks, is the GIL locked? There should be a question mark there. Is the GIL locked? It sees that it is locked, and it figures, okay, I cannot run because the GIL is held by some other thread. It will then make use some system function called cvwait to signify to the operating system that I want this operating system to wake me up once this variable called GIL is 0, and I want to be woken up either by this or when some time passes. This time is called interval. So whichever comes first, I want to be woken up, and it goes back to the waiting state. The time passes, the interval passes. No, to be precise, almost the interval passes. Before the interval of time passes, the first thread releases the GIL. It signals to this other thread that it released the GIL. Then the second thread gets woken up. It checks one thing: who was the last holder of the GIL? If it was me, if it would be me, it wouldn't lock it. But if it was anyone else, okay, the GIL is now mine. So at this point, it acquires the GIL and starts to run. And the first thread then goes to the waiting state, and the world continues. I hope it was semi-readable. Okay. And the third scenario, which is of course more complicated than the previous one. There are two threads still, but we reach the timeout called interval. So we go back to this state where the second thread is waiting for the cvwait to complete, and we reach the interval. The timeout is reached. The GIL is still locked. What happens then? The second thread gets woken up by the cvwait routine because the timeout passed. It now has a chance to set a variable called GIL drop request. This means, hey, I want the GIL. And it goes back to sleep again. It may not be entirely intuitive, but it makes sense, really. It goes back to the waiting state. At this point, the first thread continues to run, but on the very next loop of the ceval loop within the CPython interpreter, it checks this GIL drop request variable because it checks it on every turn of this loop. So the next thing the first thread does is it sees GIL drop request being equal to 1, and it says, okay, someone else wants the GIL, so I will drop it now. And it does. So the first thing releases the GIL, goes to the waiting state, red color we see. The second thread now has more chance to run, but before the first thread went to the waiting state, it did one more thing. It signaled that the GIL was released, just as previously. It also called the CVWait routine on the GIL, but with a different interval. Just as previously, this second thread checked the GIL last holder. Was it me that last held the GIL? No, it was someone else. So I can now acquire it. And in this case, it also does one more thing. It signals to the first thread that it got the GIL, and only then the first thread resets the variable, not the second one. And the loop continues. What's up with this GIL drop request being reset here? In case of two threads, it basically makes no difference who would reset it, but often we have more than two threads. And for more threads to be able to have more, for each of these threads to have some chance to run, you need this kind of cooperation. And I think it's as much as can be as much as can be packed into a presentation on the meetup. So let's stop here. But this is basically what you can read from the source code and from the comments from the source code, which you can find in these files. Oh, and at the end of the presentation, there will be a link to the slides, so these are clickable. You will be able to reach them very easily. So, with all this knowledge, if you memorized like a third of this, you would easily pass some Python hiring process. Yeah, but moving on. The GIL is there still, and of course, at least some of you heard that maybe we can get rid of it, and of course, we probably can. There are only a few expectations that needs to be met for the GIL in CPython to be removed from the source code. And one of the expectation is a very obvious one. We would remove the GIL from the code to met to have some more performance out of our code. And the obvious one is for multi-threaded code, we would expect it to run with speed, like scaling up with the number of cores. This is pretty obvious. But also there's an expectation that the performance of a single core execution won't be slower than with the GIL. Another expectation is that we won't break compatibility with 4 C extensions. We won't break compatibility of C API in CPython. And the third one is that it won't complicate the CPython code versus what we already have. So tracing garbage collection. Okay, and there were quite a few attempts really to get rid of the GIL from CPython. And first one was attempted in 1996, just 4 years after introducing threading support with the GIL into CPython. It of course failed. In 2008, there was another patch which was pretty like more complicated than the first one. The first one was just dropping, like removing the code of the GIL, and the second one was actually serious, but it also didn't met the expectations I mentioned. In 2016, when I was preparing this presentation for the first time, there was a gilectomy project, and it stopped. The project stopped just after a few months, and in 2022, there's an maybe not a GIL removal project, but very related one, using sub-interpreters and per sub-interpreter GIL to go around it. And this PEP is accepted. It's actually moving forward with the implementation. And finally, last year, there was an accepted PEP of making the GIL optional. And what does it mean, optional? There are quite a few changes in the patch related to the PEP. It touches quite a lot of subjects, just like gilectomy did, but there are changes in reference counters, in garbage collection, and so on and so forth. You can go read the PEP. It's quite long, but it's quite readable. In case you are into this level of stuff in CPython, I very recommend it. And what it boils down to, apart from changes to the code, is it doesn't just breaks the world to all the C extensions and stuff. It gives an option to not use the GIL, and it does it by a compilation flag for CPython that is basically disable GIL. And the long-term plan is, of course, to make this flag the default. And yeah, just as like I said, it was accepted. It was accepted for the very next CPython release, and from what I know, we are on track for it to be finalized. Keep in mind, 3.13 comes out in October this year. And what happened to this? Because yes, disabling the GIL breaks the C API, and it's not really. Well, let's go one by one. What changed are the expectations. It's not as if the technical stuff underneath magically changed. No, the expectations changed. The world changed. Python is much more widely used, and it's much more widely used in compute-heavy stuff. So these two things changed within the expectations. Single-threaded code must not be significantly slower. It can be slower to some degree, but not significantly. And we need to provide the gradual migration path for C extensions to adapt. And this basically means this disable GIL option. Until then, what to do? Because it will be quite a few years before the no-GIL builds will be the default ones in our operating systems. Well, it depends what we are doing. If our code is a simple, pure Python, single-threaded applications, we have nothing to do, because there's no parallelism to talk about, so it doesn't concern us. For single-threaded applications with multi-threaded C extensions, for example, if we have some software that uses NumPy, try to run it on your multi-core CPU, on your multi-core machine, look at any system monitor and check if it uses all the cores already, because chances are it just will. In case of doubt, profile your code. It's always a good idea. Some of our applications are multi-threaded, but I/O bound or I/O heavy. They use quite a lot of I/O. For example, our APIs, our web services. Start with profiling. Check where our program is slow. Chances are you would only need to add more threads at the expense of memory usage, but you will utilize all your cores with that. Some of us write asynchronous code. I've seen Starlet being mentioned in the description of the previous presentation. In that case, first thing you can try to do is run your application in multiple processes, like multiple instances of your application. Again, at the expense of more memory usage, but this is a very simple way to utilize your CPU. Profile also. See where your program is slow. There are cases where our asynchronous code uses thread pools because we may be using some libraries that are not too compatible with our asynchronous code. In this case, start with profiling, and maybe adding more threads will be just sufficient. Maybe, maybe not, but start with profiling. And finally, our real problem is where we are writing multi-threaded Python code that is CPU bound, where we want to run CPU-heavy computations using Python. Start with profiling, obviously. If that points you to the realization that okay, you cannot utilize more than some % of your CPU with only some simple changes, multiprocessing is a thing that you can think about. Sometimes it's the optimal way. Sometimes it's not. Yes. You can think about maybe someone wrote a C extension that does mostly what I want to do with Python. Sometimes it depends on what our program does, of course. You can look for the existing one, or you can start being a C expert and write your own. Maybe that's something that is feasible in your scenario. Also, there's CPython that has the no GIL, I forgot the name, not option, decorator, sorry, where you can still write Python code and wrap it, informing CPython that I don't need GIL in this section. Drop it, run some computations. Maybe that will be feasible in your scenario. And at the very last option, very sad one, but sometimes it's the best one. Look for non-Python alternatives. Sometimes this is what you would want to do. Of course, before you start writing your code to something else, compare the pros and cons and consider your scenario thoroughly. And yeah, don't forget about profiling. There are multiple profilers, including the Perf, the newest one. Yeah, I really recommend it. That's all from me. Do you have any questions?
I want you to ask one question about asyncio, because asyncio, as you probably know, there is such a function as run that accepts a coroutine. For example, we have an async function that we want to run inside our non-async code. For example, I used it once to basically inform, like make some kind of notification system inside my application. How does GIL will react to this? Like, how do this process goes in looking in your graph?
Okay, so an a simple answer would be go with profiling first. This will tell you if you profile it right, you would see, okay, this is the part of the code that is slow. How would GIL interact with that? It very, very much depends on what this coroutine and the rest of the code does. So it's, I don't think I can answer that like in abstract.
When you say profile it well, what do you mean correctly?
Using the profiler that that will basically support asynchronous code. So from what I remember, the perf should be sufficient.
Okay, thanks.
One question about multi-thread versus multi-process application. As I understand, in the multi-thread application, you can share memory between threads. And what is the biggest downside of multi-process application, except of course this memory management thing?
Like except
sharing memory.
So except exchanging the data between processes, right?
Yeah, true. Yeah.
The biggest one. No, obviously the biggest one is exchanging the data. But apart from that, from my perspective, all the rest downsides are like minuscule compared to the exchanging that. There's some overhead of memory per process, but it doesn't matter most of the time. Of course, it depends on what the program does, how much of the data it needs to exchange between these units of execution, between processes versus between threads. So here's the balance. Whether you want to utilize your CPU more, your multiple cores within the CPU more, or you want to, or you, on the other side of this balance is are the limits of exchanging data. So your memory buses or networking, if you're running these processes across machines. Yeah.
Let's suppose I want to make app which involves making CPU-bound intensive computing. You've said that it's worth using C extensions like NumPy or PyTorch. Are there any cases I can benefit from multi-thread, multi-processing on Python level instead of delegating that task to that library like NumPy or PyTorch? And furthermore, under the hood NumPy or PyTorch, is it multi-processing or multi-threading?
The second would be easier. So underneath it utilizes multiple threads in both cases. About the first one, also a balance between a few things. First being what you or your team or your company knows better, which software you will be able to maintain more easily. So this is a balance between the technical stuff, the cost of machines versus cost and knowledge of the people you are working with. So yeah, basically this. Also a balance between how well a particular C extension serves your needs. If it serves it 100%, I wouldn't think twice. If it like does tiny little bit, but all the other optimizations are, if you would need to write quite a lot of code just to use that C extension, well, it's questionable there. But there are very, very many aspects you need to consider at that point.
Okay, so if I got you right. Let's suppose I want to make inference of machine learning model with PyTorch. So PyTorch are highly optimized library, probably will do better multi-threading than me from Python level make splitting those requests into multiple Python processes.
At that point, I would look, okay, what the hardware I'm running this program on. If it is multi-core, I would start with a single process, then profile and observe the utilization of CPU. If that utilization is not what I would expect from this program, I would try multiple processes. If the parallelization of these requests are what you want, because it's not always obvious. Sometimes there are other things that make you only do like a one stream of requests and not parallel. It depends.
Okay, thanks.
Super, dziękujemy Jacku. Wielkie brawa jeszcze raz.
Dzięki.
Słuchajcie, my mamy jeszcze trochę kuponów, więc puszczam jeszcze raz. Osoby, które zadawały pytania, niech się odezwą